In lecture 4, we are going to study rotational transition. In the next lecture, we're going to study the vibrational transition, and then move on to the electronic transition, which corresponds to most of the optical transition. Okay. So you may wonder why we need to study the rotational transition when we think about the photochemistry. And actually, in photochemistry, of course, light absorption is important. And this light absorption is actually affected by the other energy levels, like vibrational states or rotational states. That's why when we need to understand the electronic transition, meaning the optical transition, you have to understand the rotational transition and a vibrational transition too. And here in this lecture, first we are going to start studying the rotational transition. As you see, this is called a rotational. Rotational means the literally when we think about the, for example, some sort of the molecules, and this molecule has some motion of state, and when we think about the rotational transition, so when we think about some of the axes and these molecules are rotating along, so depending on the rotation state, this molecule has different rotational energy. For example, if this one is rotating omega, and then there's another state of 2 omega, so faster rotation, and they have different energy. So that's what we are going to think about. Okay. Yeah. So in this section now, we have to define the rotational energy first. So let's think about these molecules, SN, and so they kind of like SN-like molecules. So the atoms are connected to each other, and when we think about some rotational axis, these molecules are rotating around, and we are going to think about this rotation of energy. And first, rotational energy, traditional way of the rotational energy can be described as E equal 1/2 I omega squared. And I is inertia moment. And omega is angular frequency. So inertia moment, maybe you studied in the mechanics. So when you have some axis of rotation, it's a kind of like rotational force. Not force, but moment, rotational moment. And then this inertia moment can be described like this. So I equal the mass of the atom times r squared. R is the distance from the rotational axis. And then you sum up all the atoms of axis from the rotational axis. Okay. So you can just do an exercise for in case of the water case. So in the case of water, you have oxygen and the 2 hydrogen, and if you take the rotational axis penetrating the oxygen, and then you can think about the rotational inertial moment of two of the hydrogen. So please stop a video and then try to calculate. Okay, then. So what you have to do is basically you have to sum up the two of the hydrogen molecules moment. So I2 and MI I squared, which is 2 MH H squared. So we have equivalent hydrogen in terms of moment, and 2H, and then RH is, of course, which is R sine Y/2 squared, and then you can calculate like 10⁻⁻27 kilogram times 94.7 10⁻12 sine 0.5, which gives 1.9 times 10⁻47 kilogram per meter squared, like this. So this inertial moment can be calculated once you define the rotational axis. And what we are doing is here, so we are trying to obtain the rotational energy, which is given by 1/2 times and I omega squared. So we just showed an example how to calculate the inertial moment in case of the rotational axis is given. Then now you can calculate the rotational energy, and what kind of the rotor you could have, as shown here. Here are the examples, and there are several different type of rotors, and also depending on the rotational axis, even for a single molecule, you have different inertial moment, meaning the different types of the energy of rotation. So in case of linear molecules, you have, if you take the rotational axis this parallel to this molecule, the inertial moment is 0, meaning that there's no rotational energy, which is reasonable because makes sense because cannot give any inertial moment. So in the case of spherical rotor, you can take 3 XYZ axis, rotation axis, but 3 inertial moment are equal. And then if you have a symmetrical one and a symmetrical one, so the independent I number is different. Now what we can calculate the total energy of rotation of energy, and which is E equal half times IX omega X squared plus IY omega Y squared plus half IZ omega Z squared. And you can convert this equation like 2IX JX squared plus 2IY JY squared plus 2 IZJZ squared, and you can define this J equal I omega, which is angular momentum. Oh. So based on this equation, you can calculate the total energy of rotation. I'm going to talk about why we introduced the angular momentum in the next page. So as we see, let's think about a simpler case. So sophistical symmetry molecule, meaning the three rotational axes are equal. So in this case, we could write like the energy is written like J squared over 2I. And here we use a replacement of J value, which was originally a continuous value in a traditional way, but here we use quantum mechanics. And there are many varieties of conversion from traditional theory to quantum theory, and this is one of them. The angular momentum J squared can be quantum mechanically. It can be replaced with J plus 1 and H bar squared. So suddenly J was originally a continuous value, but here J is an integer number. So suddenly this energy is quantized, and this kind of replacement is sometimes happen, and it is very useful. And for example, in the most famous one is like the momentum and energy. In the case of, for example, energy, you can replace like IH dt, and then also if you want to obtain the momentum, it's like the changing the 1 to ddx. So spatial derivative. So in the quantum mechanics, you need a wave function, and once when you need to obtain the physical value, you have to apply a mathematical calculation, and then you can obtain the value like energy or momentum, and like this. So anyway, in this case, the J squared is changed to J plus 1 H bar squared, which is the conversion. Just take it from the replacement from the the traditional theory to quantum mechanics. Okay, then now EJ can be replaced with J plus 1 2I H bar squared over 2I, and this one can be simplified by using HCB, where the B is defined as H bar over 4 pi Ci. Because we use HC as a kind of a unit, and B is used in you will find out this unit, and this unit can be found in the same as energy and reusable. So just try to calculate, and then rotational, or once now we can figure out so what kind of expression for the energy of rotational energy. We can calculate the transition energy of the rotation. So in this case, which is so EJ and J minus 1, which is so one energy level difference, and which is J plus 1, J minus 1 J HCP is 2 J HCB. Okay, so it means that for small b, meaning that when b is small, I is larger, so the inertial moment is larger, meaning the bigger molecules. So for the bigger molecules, B is smaller. So transition energy difference is smaller, right? So please try to calculate the CCl4, for example. Here there are the necessary values, and then you can try the calculation of how big is how big this value is.